The scientific approach to understanding the origin of life assumes that this event was and is a consequence of evolution of the elements, stars, solar system, and the development of a habitable planetary environment. A succinct definition of life is difficult due to limitations in our knowledge, but three key features for life's existence are its ability to sustain metabolism, reproduce, and evolve. No non-biological system is capable of all three processes. It is important to understand Earth's earliest environment because it set the stage for life and thus helped to define it. Shortly after its formation, 4.5 billion years ago, the solar system was probably not a stable, safe place for life. Even though the Earth accreted virtually all of its mass during the first few 100,000 years of its history, it still received periodic meteorite and cometary impacts for an additional half-billion years. The strongest evidence for such impacts comes from our exploration of the Moon, whose large impact basins were created during this early period. Because the Earth has greater mass compared to the Moon, Earth received a much larger flux of meteorites. Such cataclysms probably vaporized entire oceans and spewed out globe-encircling, life-extinguishing clouds of rock vapor. If life had begun prior to 4 billion years ago, it might have been destroyed and then recreated because no evidence of rocks older than 4 billion years has ever been found on Earth. This absence may be attributed in part to meteorite impacts. Furthermore, no rocks sufficiently well preserved to retain fossils have ever been found to be older than 3.5 billion years. Thus, the time interval needed for life to arise is constrained between the date of the last lethal meteorite impact, likely to be sometime prior to 4 billion years, and the earliest well-documented fossils, which are 3.5 billion years old. Fossils reveal that life has survived for perhaps 80% or more of Earth's 4.5 billion year history, and that life may have accompanied the earliest stages of a planet's development. Insights into the early history of planets come from a variety of sources. Fossil studies help us determine the ages and the paleoenvironments associated with evolutionary advances. Geological observations of Earth and other planets reveal the nature of the earliest environments. Biochemical analysis of bacteria tell us about the genealogy of life by establishing the sequence of events in biochemical evolution and thus identifying attributes of microorganisms which are truly ancient.
DNA is a storehouse of information about life. It contains everything within it that's needed to make a cell. Furthermore, the replication of DNA is very much involved with the replication of living cells themselves. So this characteristic, together with this tremendous abundance of information, has led many to propose that the DNA molecule is essential for the origin of life itself. Now, the molecule is a really interesting one. As you know, it's a helical shape. It can be quite long. In fact, some bundles of DNA can be seen under the light microscope. And of course, this gives rise to a question, and that is, how could this very complicated, long, large molecule arise in a non-biological, relatively uncontrolled environment? In fact, for many decades now, people have tried to simulate the synthesis of DNA under reasonable conditions and have not been able to do so. So it gives rise to the question, was there some kind of a special environment required for the first DNA molecule to appear? Another idea has been proposed in recent years that's interesting, and that is that, well, perhaps cell-like structures were the first entities, that they are formed from molecules called fatty acids, which have been found in non-biological environments. They've been actually found in meteorites. And so therefore, perhaps these cell-like vesicle structures were very early arrivals on the scene as far as the origin of life is concerned. And perhaps within these vesicles you had chemical reactions beginning, which were sort of like some of the metabolic reactions that we see in cells, and that perhaps within this environment, DNA and its very complex system of replication first arose. So this is another idea now which is being subjected to a lot of experimentation. When you compare that idea to the original idea that DNA was ancestral to life, you see that there's really quite a range of opinion as to what the earliest events in the origin of life might have been. And so I think over the next few years, as we see these two different ideas being pursued, we'll learn a lot more about these earliest events associated with the origin of life, and I'm sure there'll be a lot of surprises that we'll discover along the way.
One key revelation has been that life consisted solely of single-celled microorganisms for most of its history. The oldest conclusively identified fossils of plants and animals are less than 500 million years old. During the Earth's history, major environmental changes were driven by the evolution of the planet and the sun. These changes probably in turn influenced biological evolution. For example, our sun's luminosity increased as much as 30% during its lifetime. The luminosity increase implies that for oceans, rainfall, and moderate temperatures to have existed as they have since at least 3.8 billion years ago, the composition of Earth's atmosphere, such as its greenhouse properties, must have also changed dramatically during its history. The solid Earth also evolved. The core and mantle were heated initially by the energy released from the impacts of meteors that formed the planet, and heated later by the decay of radioactive elements such as uranium, thorium, and potassium. As this heat escaped through the Earth's crust, it sustained volcanic activity, outgassing, the movement of crustal plates, and the evolution of a relatively buoyant continental crust. Earliest Earth probably had a global ocean with clusters of volcanic islands and small continental land areas. The chemistry of the atmosphere and the oceans was likely dominated by volcanic activity, which was much more active then than it is now. Volcanic emanations such as carbon dioxide and ferrous iron and sulfide gases were much more widespread. However, free oxygen was in very short supply. Furthermore, genetic studies of RNA reveal that organisms capable of photosynthesis, carbon dioxide fixation, uptake of organic substances, and tolerance of elevated temperatures already existed early in the history of life. Ancient fossils include discrete remains of both individual cells and stromatolites. Stromatolites are built microbial communities, which typically form laminated, carbonate-rich sediment. The best preserved 3.5 billion-year-old fossil remains are found in the Barberton Mountains of eastern South Africa and the Pilbara block of northwestern Australia. 3.5 billion years ago, these stromatolites had already colonized coastal marine environments. They were photosynthetic and developed resistance to ultraviolet light and periodic desiccation. The earliest photosynthetic bacteria were incapable of producing oxygen as a byproduct of photosynthesis, and we do not know whether 3.5 billion-year-old communities possess this capability. However, life had apparently become remarkably sophisticated and diverse, which implies that the biosphere might be considerably older than 3.5 billion years. In fact, severely degraded organic remains can be found in 3.8 billion-year-old rocks from Greenland. This suggests that life arose in just a few hundreds of millions of years or less when the last life-extinguishing meteor impacted the Earth. Volcanic environments, such as thermal springs, played an important role for ancient communities. RNA studies have identified that tolerance of elevated temperatures is an ancient characteristic. Many of the more primitive, non-oxygen-producing photosynthetic systems utilize hydrogen sulfide, a constituent of thermal waters, which was probably never pervasive in sunlit shallow waters of ancient oceans. Thermal springs on the floor of deep ocean basins have been identified as potential refuges for the survivors of large meteorite impacts. Fundamental changes occurred in the environment of the oceans and atmosphere between 3.5 and 1.5 billion years ago. These changes were driven by warming of the sun, gradual decline of volcanic activity, and the stabilization of continents. Driven by trends in solar luminosity and volcanic activity, atmospheric levels of carbon dioxide, a key gas for sustaining the greenhouse effect on Earth, declined from perhaps several tens of percent by volume to less than 1%. A warming sun could have accelerated the removal of carbon dioxide by enhancing the rate of rock weathering.
The atmosphere has changed dramatically through time, through the history of the Earth. We're pretty convinced of that. And one way to understand these changes is to understand the additions that can be made to the atmosphere and the subtractions or the sinks that can remove gases from the atmosphere. Additions, of course, in the early days would have been impacts of meteorites and comets bringing in material. Also, the outgassing of volcanoes would have been another source. And of course, to the extent that there were organisms early in the history of the Earth, they could be sources of gases as well. Sinks, things that remove gases from the atmosphere, would be in some cases very large impacts of meteorites, literally blasting the gas away from the Earth. Another sink, of course, would be the reaction of these gases with the surface of the Earth, a process we call weathering, removal of gases by that mechanism. And then the third mechanism for removing material would be organisms, again, taking up certain gases. One way to illustrate some of the changes that we thought were really substantial over time would be to talk about the gases of carbon dioxide and oxygen, free oxygen. Carbon dioxide is a gas that we think was very abundant in the early history of the Earth, perhaps as abundant as oxygen is today in the atmosphere, about 20% or so. We had a lot of CO2 at that time because comets probably brought it in. Also, a lot of volcanic activity would have caused it to outgas into the atmosphere. And it was a good thing we had a lot of CO2 back then because the sun was a little less luminous. And this additional CO2 would have helped keep the climate at a point where we had liquid water, which we, of course, feel is essential for life. And then over time, as volcanic activity declined and the weathering reactions continued, this CO2 dropped to levels that are quite small today, a fraction of a percent, about 0.03% or so. And so this is the basic story with carbon dioxide. Now, oxygen is interesting because it's just about the mirror image of that. In the early days, we think there may not have been much oxygen at all. The principal reason for that is that the major source of oxygen is life, today anyway, and the process that produced oxygen and caused it to accumulate in the atmosphere might not even have existed prior to 4 billion years ago, and we know that the Earth is about 4.5 billion years in age.
As the continents coalesced and stabilized, they created broad, shallow seas, whose sediments became populated with diverse photosynthetic stromatolitic communities. One exceptional early example of such an extensive continental shelf is the 2.5 billion-year-old Transvaal group of South Africa. Communities such as those whose fossils are found in the Transvaal rocks produced abundant free oxygen. Between 2.5 and 1.5 billion years ago, atmospheric oxygen levels rose, and the oceans became more oxygenated. Evidence of banded iron formations from less than 1.7 billion years are rare, because such formations require iron in a reduced state, and hence an oxygen-free deep ocean. 1.5 billion years ago, the Earth's crust, oceans, and atmosphere were strikingly similar to today's world, as was the nature of life itself. The interval between 1 billion and 500 million years ago witnessed dramatic change, both in atmospheric environments and in biological evolution. The largest glaciations ever known periodically stretched remarkably close to the equator. A supercontinent became fragmented and spawned the individual continental masses, which can actually be traced to those on modern Earth. Chemical analysis of limestone revealed that the rates of synthesis, degradation, and burial of organic matter in sediments might have experienced wide fluctuations. The cause and effect of these developments are still uncertain. However, the dramatic increase in atmospheric oxygen facilitated the evolution of fully assembled eukaryotic cells about 2 billion years ago. These new cells created species that ultimately led to the evolution of multicellular terrestrial plants and animals within the last 500 million years. However, the evolution of life was hindered by atmospheric upheavals, which may explain the extinction of dinosaurs 65 million years ago.
You have this impact, it strikes the ground, makes a crater, and material is ejected, blown around the world, flies around the world by gravity, re-enters all over the world and like meteors. And all these meteors combined make a sky that looks like magma, red hot, and sets the world on fire. We actually have evidence that the world was set on fire because in this global layer of clay that has all the iridium also has a lot of soot in it. Quite a bit of soot, apparently. And the amount of soot is about what you would get if you burned the world's trees, burn the world's biomass, set it on fire, and you'd get a lot of soot. So for the months after the fire and after the impact, things would be pitch dark. And any dinosaur that survived the fire would then have to avoid walking into trees, stepping in the holes, have to be able to find food. And dinosaurs apparently were diurnal creatures. They were visual and they walked around in daylight. And they were really at a severe competitive disadvantage. The general trend, to the best it's understood right now, is that those creatures that survived were creatures that tended to live at the bottom of the food chain. Detritus feeders did okay. Freshwater swamps did fine. Apparently the food chain in a freshwater system is dominated by detritus washing into the lake. So it seems that freshwater fish did okay. It seems that things like crocodiles did okay. But the dinosaurs apparently were not in that ecosystem. They apparently were more out there on the land, and they did not do okay.
Impacts of comets and meteors may destroy large continental areas through blast waves, earthquakes, fires, and tidal waves. When a large 150 to 300 kilometer in diameter asteroid hits the Earth at a velocity of 40,000 miles per hour, it creates an enormous ejecta cloud, which explodes outward into space. The sky would turn from its normal transparent blue to a brilliant red. During the following hour or so, the red sky would cool, plunging the world into total darkness as the asteroid remnants blot out the sun. Vast billows of smoke would fill the sky from large continental fires. The loss of sunlight would blacken the sky for months. The light loss would be so enormous that it could cease photosynthesis. However, we hope that we will not determine the implications from first-hand experience of the inevitable collision between Earth and another massive asteroid. Our research and discoveries about evolution of life on Earth offer valuable lessons as we contemplate the exploration of Mars. The two planets are indeed different, but perhaps these differences have never been so striking as they appear today. Earth and Mars might have been more similar in the past. However, the inevitable climatic deterioration into coldness and dryness might well have extinguished the Mars biosphere. This very underabundance of geological activity, which caused the climate to deteriorate, also enhanced the chances for preserving an early fossil record on Mars. Although a biosphere might have died on Mars, it perhaps left clues for understanding the birth of the biosphere on Earth. Today, it is a commonly held scientific belief that life, including intelligent life, exists on other planets orbiting other stars. The scientific community has begun an attempt to find ways to substantiate this belief. The purpose of SETI, or the search for extraterrestrial intelligence, is to detect evidence of such intelligent life in our Milky Way galaxy. One of the earliest documented ideas about the existence of extraterrestrial intelligence dates back to over 2,000 years. In the 4th century BC, the Greek philosopher Metrodorus said, "To consider the Earth as the only populated world in infinite space is as absurd as to assert that in an entire field of millet only one grain will grow." Despite such an early claim to the existence of life elsewhere, there were very few proponents of the existence of extraterrestrial life until the 15th and 16th century, when Copernicus and Galileo challenged the Ptolemaic view of Earth as being the center of the universe. In 1959, a new field of science called exobiology emerged. Exobiologists study, among other things, the origin and evolution of life. In studying the chemical origin of life, exobiologists theorized that all living things originated from inanimate matter. They also discovered a large number of carbon-based interstellar molecules and suggested that life forms, based on a molecular structure similar to ours, may have evolved on planets revolving around other stars. These theories on the origin of life fueled the argument for the existence of extraterrestrial life forms. If the same raw material leading to life on Earth exists on other planets, it seems logical that life can also evolve on these planets given the appropriate conditions.
Everything we have learned in our study of the cosmos, of the origins of life, of the evolution of life, have suggested that the processes which caused us to be here are completely normal processes in the evolution of stars and planets and eventually biology. No freak circumstances were required for us to be here with our high technology. and therefore the steps which led to our existence should have occurred in many, many places.
With the realization that the origin and early evolution of life can be universal, people started speculating that there may be other forms of intelligent life throughout the galaxy. The new challenge was to find ways to detect these life forms. Given our present level of technology, detection of other life forms is extremely difficult, and traveling to other stars is presently impossible. Even if we were able to develop the technology to travel near the speed of light, it would take at least a few decades to reach stars that exist many light years away. Such a long voyage would require so much energy and supplies that it would be difficult to accomplish. Instead of relying on future technology, we try to work with a technology that we already have. One such technology gives us the ability to detect electromagnetic signals at great distances from our planet. In 1959, Cocconi and Morrison published a paper proposing the use of radio telescopes that would search frequencies near the hydrogen line of 1420 megahertz to detect extraterrestrial civilizations. Following this publication, an astronomer named Frank Drake independently carried out the first search for extraterrestrial intelligent life in 1960 by aiming a radio telescope at 2 nearby stars. This technique of searching for signs of extraterrestrial life set the foundation for the SETI program. In 1971, NASA first showed interest in the search for intelligent extraterrestrial life when it published Project Cyclops, a design study of a system for detecting extraterrestrial intelligent life, co-authored by Barney Oliver and John Billingham. Over the next 20 years, NASA developed its own SETI program, which became known as the NASA High Resolution Microwave Survey. Then, in late 1993, the SETI Institute, a privately funded nonprofit research organization in Mountain View, California, undertook the search, now called Project Phoenix. Although there are additional SETI programs in several countries, Project Phoenix is by far the largest search now being undertaken.
One of these days, we may actually detect a signal from an extraterrestrial civilization. All those with interests in life in space are going to be very fascinated with the discovery of what their chemistry is, what their biology, what their evolutionary processes are, and of course what their intelligent species is actually like. But it's not just an interest from the point of view of the scientist. Whatever walk of life you come from, be it from the arts or philosophy or history, religion, they will have their own variety and version. It's going to be different from ours. So it's going to be just a fascinating discovery.
Researchers at the SETI Institute believe that if civilizations are technologically advanced, they will emit radio waves of frequencies similar to those used on Earth. SETI scientists aim to detect these radio waves using large radio telescopes. However, the question of probability arises. Will chance be in their favor? And will they be able to detect anything in such a vast galaxy? One way of estimating the distribution of technological societies on other planets is to use the Drake equation. This equation, presented by Frank Drake in 1961, is used to calculate the number of detectable civilizations in our galaxy. The equation states that N is equal to the product of R, Fp, Ne, Fl, Fi, Fc, and L, where N is the number of civilizations in our galaxy whose radio emissions are detectable. Although values for the variables are probabilistic, SETI researchers have made estimates of these values based on careful evaluation of available facts. The first variable, R, is the rate of star formation in the galaxy per year. The value used for R is 20 per year, which is known to be reasonably accurate. The value Fp refers to the fraction of suitable stars that have planetary systems. Not all stars are suitable to bear planets. Stars range in size from the large O stars to the much smaller M stars that are barely large enough to have nuclear reactions. M stars do not radiate enough energy, and O stars have so much energy that they destroy themselves before the evolutionary process of life on planets has time to occur. The ideal stars are the F, G, and K stars that have masses close to that of our Sun and that can irradiate planets to temperatures that are suitable for life. However, not all FG and K stars necessarily have stable planetary orbits, since many stars belong to binary or multiple star systems. SETI scientists estimate that about 50% of the FG and K stars will be good suns and have planets with stable orbits. Since FG and K stars make up about 20% of all stars, then the value of FP turns out to be 0.2 times 0.5, which gives us an FP value of 0.1. The next variable, NE, refers to the average number of planets within these stable planetary systems that are ecologically suitable for life. The presence of liquid water on a planet is often considered a good criterion for whether or not the planet will be suitable for life. In our solar system, there is a region known as the circumstellar habitable zone. It is believed that if a rocky planet is in this region, it will be able to sustain life. Notice that Earth is in this region and that Mars is also on the border of this region and may have sustained life in the past. Due to the lack of astronomical evidence, SETI scientists base their value of NE on our own solar system that has at least one life-sustaining planet. It is therefore assumed that the average number of Earth-like planets per good sun is equal to 1. Computer simulations of planetary systems produce the same values. The term FL is the fraction of these Earth-like planets on which life begins. Presently, most exobiologists believe that if a good sun and a good Earth have evolved, then life will begin, so FL is chosen to equal 1. Fi refers to the fraction of these planets on which life actually gives rise to intelligence. The type of intelligence that concerns us is the cognitive type of intelligence possessed by human beings, and some estimate this value to be 0.05. Fc is equal to the fraction of such planets in which the intelligent life evolves to an advanced communicative technology. Most people argue that the probability that communicative technologies will arise from intelligent life is very high. Therefore, they choose Fc to be equal to 1. L, the final variable in the Drake equation, refers to the average longevity of civilizations in the galaxy. Its value is the most subjective in the equation, and hence the most difficult to predict. Some choose it to be 10 to the 6th, while others, who are more skeptical, choose much lower numbers. It is now 1996, and we have been in the category of an advanced communicative civilization for just over 60 years, and some argue that we will not survive for much longer. Therefore, we sometimes leave the value for L blank, and then see how N varies when we substitute different values for L. Based on the resulting value of N, we can calculate the mean distance between communicative civilizations in the Milky Way galaxy. Using the values previously given, our calculation for the value of N is equal to 0.1 L. The following table demonstrates the different N values and mean distances we get when we select a range of L values. For example, if we chose the mean longevity of a civilization to be 1,000,000 years, then we can calculate that there are 100,000 civilizations in our galaxy and that the mean distance between civilizations is 464 light years. This number also tells us that it will take 464 years for the signal to reach the Earth. Notice from this table that any civilizations that SETI actually detects will be much older than we are. We have only been able to send out strong radio signals for a few decades, so we are in our infancy. Viewed against the geological timescale, we are therefore the youngest technological civilization in the galaxy.
Any society that we discover will be much older than we are, perhaps 1,000,000 years, perhaps 10 million. So we'll be able to learn a lot from them. They will be probably more advanced, and they will have passed through the same early stages that we're going through now, and they will have emerged a long time after that with a stable and long-lived society. Perhaps this gives us some hope and comfort for our own progress towards such stability and longevity in our own society.
Due to the low probability of signal detection, SETI scientists and engineers have had to devise a technique of maximizing detection. This is done by optimizing targets, maximizing sensitivity, and optimizing signal detection. To optimize targets, SETI selects particular stars that fit certain criteria. These stars must be nearby, older than 3 billion years, and mostly single FG or K stars. Nearby stars are targeted because their signal will be stronger and take less time to reach the Earth. Stars older than 3 billion years are used because, based on our own planet, it might take at least 3 billion years for civilizations with communicative technology to evolve after the formation of a star. The targeting of single F, G, or K stars, as explained earlier, is based on their likelihood of sustaining planetary systems. In order to maximize sensitivity, SETI researchers use large radio telescopes, low-temperature receivers, long observation times, the microwave region of the spectrum, and narrow band detection, which allows one to distinguish technologically generated signals from the broader band emissions of natural astrophysical processes. The larger the radio telescope, the greater the probability of picking up a signal. Presently, the largest antenna used is located in Arecibo, Puerto Rico. The terrestrial microwave region is significant.
There is a preferred region in the electromagnetic spectrum, we believe, that minimizes the energy required to make contact, and that is in the microwave region. And the reason for that is that the noise that would interfere with our transmissions, or theirs, is lowest there.
This figure illustrates a measure of the temperature depicted as noise at different frequencies of the electromagnetic spectrum. The purpose is to make sure that the search is at a frequency where there is low noise, so we can distinguish a signal from the background. In the lower frequency end of the EM spectrum, there is a high degree of noise due to radiation from the galaxy. In the higher frequency end of the spectrum, there is also a high amount of noise due to the presence of oxygen and water in the atmosphere. The best region turns out to be that part of the spectrum between 1 and 10 gigahertz. This region is called the microwave window. In order to optimize signal detection, SETI investigators use all polarizations, multi-channel spectrum analyzers, Doppler drift detection, continuous wave detection, pulse detection, automated analysis, radio frequency interference or RFI rejection, follow-up detection, and confirmation by one or more separate observatories elsewhere. Doppler drifts are apparent changes in frequency due to the movement of the source towards or away from the observer. They need to be taken into account due to the rotation of planets. Therefore, if electromagnetic waves were emitted from a source on another planet, the frequencies would appear higher when the source was moving towards the Earth and lower when moving away. SETI solves this problem by looking for a very large number of different frequency drifts between +1 Hz and -1 Hz. Follow-up detection devices and radio frequency interference rejection strategies are very important for the avoidance of misinterpreting signals. The devices that analyze the spectrum look for peaks above the background signal as an indication of a technology-generated signal. However, even though SETI systems have detected a number of such signals, subsequent analyses have shown that these signals were all generated on Earth. SETI observers also attempt to avoid these interfering signals by selecting an isolated location for the receiver. An ideal location is on the far side of the Moon. Since this region always faces away from the Earth, Earth-generated signals would not reach the detectors. The overall prototype of the Project Phoenix system is as follows. The antenna picks up the incoming waves and sends the signal to the radio frequency subsystem. The radio frequency subsystem sends the input to the multi-channel spectrum analyzer, or MCSA, that has 28 million separate individual channels. Its output is then sent to the signal detection subsystem that looks at all channels to see if there is a strong signal. Strong signals, which appear on the monitor as spikes, are then sent to the data collection archive subsystem, which stores the information. On receiving a signal, the SETI scientists are alerted and follow procedures needed to verify the signal. Until present times, all of the strong signals detected by Project Phoenix have come from the Earth. However, let's imagine that one of the signals does appear to be real. In such a situation, the SETI scientist will then contact other observatories with radio telescopes and give them all the signal characteristics to find out if they can also detect this signal. After weeks of verification, much effort might have to be put into interpreting the signal. There is always the possibility that these signals could carry a message. A civilization less than 30 light-years away could have detected one of our strong radio waves and responded. Signals from civilizations further away could also carry messages, but they might not.
One of the questions that we're often asked is, what do you do if you actually detect a signal? And this is more complicated than it looks at first glance. Most SETI scientists take the position that any signal we detect is automatically the property, as it were, of all humankind. And therefore that we should instantly tell everyone and invite everyone to study the signal and take it from there.
Evidence for the existence of extraterrestrial intelligent life will have important consequences. Because of the profound implications of initiating two-way communication with an advanced civilization, we must consider whether or not to respond and how to respond. Because we cannot predict the nature of the signal, it is difficult to determine a response until after a signal is received. The response that we transmit will depend on a number of factors, including the type of signal and the content of any message. However, it will also largely depend on our own reaction to the knowledge that extraterrestrial intelligent life really exists. Let's begin by reviewing the normal functions of the cardiovascular system. More than 70% of the body is composed of constantly circulating fluids, primarily blood and tissue water. While much of this fluid lies inside the body's cells, an important part of it lies in the extracellular compartment, which includes the blood. A complex system of checks and balances makes it possible for the body to move blood and extracellular fluids up to the head and down to the feet while functioning in normal gravity. The cardiovascular system, which includes the heart, the blood, and the blood vessels, is the part of the circulatory system that transports blood throughout the body. Working as a pump, the muscles of the heart push blood through the blood vessels to perfuse both systemic and pulmonary circulations. Pulmonary circulation contains blood that flows through the lungs to pick up oxygen and get rid of carbon dioxide, while the systemic circulation contains all other blood flow pathways in the body. The arteries are tubes that transport blood to the tissues at high pressure. Arterioles act as control valves, regulating blood flow through the capillaries. Capillaries are the narrow, thin-walled vessels that support the exchange of gases, nutrients, and wastes between cells and blood. Veins have thin walls, which can expand and contract as they transport blood from the tissues back to the heart at variable pressure. These vessels have higher compliance than the arteries. Factors influencing arterial blood pressure include the pumping force of the heart, blood volume, resistance to flow, and the viscosity of the blood. Gravity also has a direct influence on blood pressure and flow in the body. When a person is standing, gravity helps pull the blood downward to the lower extremities. When we walk or move our legs, the muscles contract, forcing blood up through the veins of the calf towards the heart. The valves in the veins ensure that the blood flows in one direction, thus counteracting the force of gravity. Since every organ in the body interacts with the cardiovascular system, small changes in this system can ripple throughout the body. Let's turn our attention to the changes produced in the cardiovascular system when the force of gravity is removed. In space, since gravity no longer pulls blood and fluids down to the feet, there is an immediate fluid shift towards the head. This headward fluid shift can cause discomfort and other problems for astronauts during initial exposure to microgravity. The increased blood volume in the head and trunk also initiates cardiovascular adaptation, such as reduced plasma volume. In simulated microgravity experiments on Earth, the kidneys respond to accumulated fluids by increasing urine production. However, this increased urine output has not been observed during spaceflight, probably because most astronauts intentionally dehydrate themselves prior to spaceflight. Other physiological systems are also affected as the body adapts to weightlessness. Losses of muscle and bone strength decrease the body's weight-bearing abilities. These effects are more pronounced during spaceflights that last more than a week. Also, the blood system shows a decrease in red blood cell count and a decreased immune system response. How do microgravity-related changes in the cardiovascular system affect astronauts? Some changes are fairly benign, while others could present serious problems in emergency situations. The most obvious physiological change astronauts experience is facial edema, or swelling, which occurs immediately after entering orbit. Compare this astronaut's normal face with his puffy face during flight. During microgravity, astronauts' legs actually change shape, taking on a skinnier look that they call bird legs. Many astronauts also experience space motion sickness, which could be exacerbated by headward fluid shift. And furthermore, astronauts have reduced capacity for exercise during spaceflight and for 2 weeks following spaceflight. Headaches are another problem in microgravity. Astronauts' headaches can be pulsating due to higher blood pressure in the head when gravity is lost, and may last for several days during flight. Finally, crew members returning from both short and long duration space flights experience post-flight orthostatic intolerance, or hypotension, because of reduced blood pressure and flow to the head. This dizziness or faintness upon standing may be caused by the lower blood volume, a rapid shift of blood towards the feet, or the inability of the body to sense and compensate for changes in blood pressure.
About half the astronauts experience orthostatic intolerance when they come back to Earth. What this is when they're exposed to the 1G field, the blood tends to move back down towards their feet. So they have less blood pressure and less blood flow to their head. So when they come back to Earth, about half of the astronauts either feel faintness, nausea, or are unable to get into an upright posture. This is important because the astronauts have to be fully functional when they get off of the orbiter. They have to perhaps perform any emergency egress due to a fire or some other unforeseen accident. Right now, it takes about half of the astronauts 1 to 2 hours to be able to stand up and walk off the orbiter. This is after a 1 to 2 week shuttle flight. For longer flights, for example, the cosmonauts who've been in orbit for up to a year, when they land, they have to be carried out of their return vehicle, put into a reclining chair and kept there for 3 or 4 days before they can assume upright posture and start to move around.
Let's take a closer look at the physiological mechanisms associated with these problems. On the left, you see the expected distribution of tissue fluid and mean arterial pressure at head, heart, and feet during pre-flight standing posture on Earth. Note that the pressure is greatest at the feet and lowest at the head. During microgravity, all gravitational blood pressure gradients are lost, and only viscous blood pressure gradients exist between arteries, capillaries, and veins. This results in the headward fluid shift. Blood pressure and volume are reduced in the legs and increased in the head. This fluid shift accounts for the facial puffiness and bird leg syndrome. Loss of gravitational pressures increases capillary pressure in the head and filtration of plasma into the extracellular compartment, which may cause intracranial edema. The increased intracranial pressure may reduce brain perfusion and oxygenation and often causes headaches. Under normal conditions, the cardiovascular system works this way to prevent edema. When precapillary sphincters sense an increase in arterial pressure, they contract to slow down or even occlude the arterial flow. Fluid tends to move out of the permeable capillaries, bringing important nutrients and oxygen to surrounding tissue. Fluid then moves into the lymphatic system and returns into the venous system via the thoracic duct. This process is what maintains our normal fluid balance, especially in the lower body. Fluid transport between the capillary blood and interstitial fluid, that is in the space between cells, is governed by the Starling equation. The equation describes fluid movement across the capillary wall due to pressure inside the capillary or outside the capillary wall. The 4 Starling pressures are blood pressure inside the capillary, colloid osmotic pressure caused by proteins, primarily albumin in the blood, which tends to draw fluid into the capillary, interstitial pressure outside the capillary wall, which could be slightly positive or negative, and colloid osmotic pressure in the interstitial fluid, which tends to draw fluid into the interstitial space. To investigate the fluid shift experienced in space, microgravity is simulated on Earth by a 6-degree head-down tilt. Placing a person in this position for a period of time causes a fluid shift similar to that experienced in microgravity and produces many of the same problems described earlier. To help scientists understand facial puffiness, 7 volunteers were placed in 6-degree head-down tilt for 8 hours. All 4 stalling forces which govern fluid flux in and out of blood vessels were measured periodically. The findings indicated that capillary blood pressure increased. Blood colloid osmotic pressure decreased during the first 4 hours. Interstitial and colloid osmotic pressures did not change significantly. It was therefore determined that the transcapillary pressures that contribute to facial edema during head-down tilt include increased capillary pressure in the head and decreased capillary pressure in the feet. Decreased capillary pressure in the feet causes greater reabsorption of tissue fluid into the blood, which in turn reduces intravascular protein concentration and blood colloid osmotic pressure. The headward fluid shift can also lead to a possible decreased baroreflex response and reduced plasma volume. Baroreflexes are reflexes mediated through nerves in various blood vessels in the intrathoracic and cervical areas and in the heart. They are sensitive to volume and pressure changes within the vessel. Here's how it works. An increase in blood plasma volume in the thoracic region activates the Henry Gower and other related reflexes. These reflexes cause atrial distension and increased atrial natriuretic peptide secretion. At the same time, increased upper body blood pressure causes reduced vasopressin secretion and sympathetic nerve activity in simulated microgravity. The reduced sympathetic activity decreases renin-angiotensin-aldosterone production, which increases urine output and reduces plasma volume. Reduced plasma volume can reduce the astronaut's ability to exercise during flight due to reduced blood perfusion. Interestingly, while a headward fluid shift during head-down tilt on Earth causes an increase in central venous pressure, studies have shown that in space, the fluid shift reduced the central venous pressure. At the same time, the size of the heart increased. In order to ensure the safety and quick recovery of crew members following spaceflight, it is crucial that we develop effective countermeasures to help astronauts avoid microgravity-induced problems. Scientists have studied giraffes and snakes to investigate how their unique body structures have adapted to special demands placed on them by Earth's gravity. For example, a 5-meter-tall giraffe may have a blood pressure gradient from 70 millimeters of mercury at the head to 400 millimeters of mercury at the feet. Why doesn't this high blood pressure increase downward blood flow and swelling of the feet? Giraffes have developed protective mechanisms that enable them to prevent edema. These include tighter skin, thicker smooth muscle and capillary basement membranes in their leg arteries, prominent lymphatics and muscle contraction of the precapillary sphincter. In essence, giraffes have developed their own pressurized anti-gravity suits. Some species of snakes have also caught the interest of scientists because of their seeming ability to defy gravity. How does a snake sustain adequate blood pressure to both its head and tail when moving vertically? Studies have shown that the position of the heart and lungs differ among species. Aquatic, semi-aquatic, terrestrial non-climbing, and terrestrial tree-climbing snakes have each adapted to the demands made on them by gravity. Arboreal snakes' tight skin and efficient muscle movements also help prevent blood pooling when they climb trees. Their reaction to being placed in an altered gravitational pull may provide important data to help develop useful countermeasures for humans after spaceflight. Currently, astronauts on 1 to 2 week missions use the following countermeasures to minimize the effects of microgravity during spaceflight. Astronauts enter a lower body negative pressure chamber, or LBNP, for 4 hours, where negative pressure equals minus 30 millimeters of mercury. During this time, they ingest salt tablets and water, which equal 1 liter of saline solution. The negative pressure draws the blood and tissue fluids down towards the legs, simulating gravity. The oral saline ingestion may help rehydrate the body so it's ready to readapt to Earth's gravity. This method is called an LBNP soak. Another LBNP countermeasure involves wearing a suit that generates blood pressure gradients inside the body, similar to those in an upright posture on Earth. Development of techniques to provide Earth-like blood pressure gradients from head to feet are important for longer duration missions. Long and short arm centrifuges are also being experimented with to help provide a blood pressure gradient. Finally, aerobic exercise may provide a useful method to help maintain heart function and plasma volume. It is hoped that research pursued in the space environment will help us to understand many ailments suffered by people on Earth, such as hypertension and other heart and cardiovascular problems. Let's look at a few examples. Studies of fluid shifts and hypotension may lead to measures to help prevent hospital patients from fainting when they get out of bed. The development of a chemically balanced rehydration fluid called AstroAid may prove useful in oral rehydration of patients. Miniaturized cardiovascular instruments have been developed for intracranial pressure and blood pressure, echocardiography, and other cardiovascular functions. Anti-gravity suits have led to leggings that aid venous return and help heal leg sores in the elderly. And video conferencing links help doctors and scientists bring modern diagnoses and research results to remote areas on Earth. All terrestrial animals, especially taller, upright, and heavier species, such as humans, are well adapted to movement in Earth's gravity. Their musculoskeletal systems have adapted to meet the demands of their environment. One important environmental factor is gravity. When the physical environment is altered, as during exposure to weightlessness, the musculoskeletal system adapts to meet the changes. Muscles are the most adaptable tissues in the body. Muscle architecture, fiber type distribution, tendon length, fiber diameter, and fiber length can all be altered to adjust to the applied stimulus. Muscles generate force and movement by contraction. Although muscles perform a single action, the body has different tasks that muscles must accomplish. Hence, there are three types of muscle: cardiac, smooth, and skeletal. Cardiac muscle is found only in the heart. Smooth muscles line all internal organs and the blood vessels that fuel them. Both of these muscle types are involuntary. Skeletal muscles carry out voluntary actions. Skeletal muscle is comprised of slow and fast twitch fibers. Muscle fiber diameter determines its strength. Muscle length determines fiber contraction velocity and the distance over which the fiber can shorten. Skeletal muscle fibers are designed to produce force, to work, and to sustain this effort over time. Force is produced by cyclic interactions of contractile proteins, myosin and actin, which form into parallel arrays of overlapping thick and thin filaments. The interactions couple chemical energy via hydrolysis of adenosine triphosphate, or ATP, to produce force. When muscle fibers are stimulated, calcium ion concentration in the myoplasm surrounding the filaments is increased. The calcium ions bind to actin. The interaction between actin and myosin is modified so that the muscle can produce force. The musculoskeletal system adapts to a weightless environment successfully, but in so doing, weight-bearing muscles, cartilage, and bones are weakened. The weaknesses pose few problems as long as the astronauts are relatively inactive in weightlessness. However, heavy work in space may cause muscle tears or bone fractures. Upon returning to Earth, readaptation to our gravitational environment is a long, arduous, and risky task. Some musculoskeletal adaptations of humans that are associated with microgravity are muscle atrophy, reduced muscle tone and strength, increased muscle fatigability, reprogramming of muscle synergism, reduced motor control, motor end plate degeneration, increased contraction velocity, bone demineralization and bone mineral redistribution, connective tissue degeneration, and back pain. Adaptations associated with the musculature during exposure to microgravity. The most significant muscle-related adaptation associated with exposure to microgravity is atrophy. When a load-bearing force, such as gravity, is significantly reduced or eliminated, there is partial loss of all proteins. and preferential loss of contractile proteins, as well as muscle atrophy. Muscle atrophy is especially common in slow-twitch anti-gravity muscle fibers, such as leg, back, and neck muscles. Other significant adaptations include decreased muscle tone and strength. Results from tests conducted 4 to 5 days following Skylab missions indicate that leg extensor strength decreased on the average by 10 to 16% compared to pre-flight values. Strength and tone also decreased in lung muscles of the back, as well as in the chest and abdominal muscles. Physiologic mechanisms that may explain some of the muscle-related adaptations associated with microgravity. During exposure to microgravity, there is loss of static and dynamic loads along the longitudinal axis of the body. Cephalid fluid shift and alteration in blood pressure, flow, and interstitial fluid pressure. These factors are primarily responsible for changes seen at the tissue level. Muscle atrophy is determined by obtaining small samples and by magnetic resonance imaging of astronauts after returning to Earth. Cross-sectional area and leg volume of the soleus and gastrocnemius muscles, as well as the total leg compartment, were evaluated before and after 9 days of microgravity in 8 astronauts. Leg muscle volume was reduced significantly by 5.8% in the soleus, 4.0% in the gastrocnemius, and 4.3% in the total leg compartment. Evidence suggests that loss of muscle strength and reduced tendon mass were largely due to decreased protein synthesis in response to the low loading conditions in space. Reduced protein synthesis is caused initially by reduced translation and secondarily by reduced transcription of some proteins. Results gathered during and immediately following long-duration spaceflight include negative nitrogen balance, minus 4.5 grams per day, decreased total body potassium, increased plasma amino acids, increased blood levels of creatinine and 3-methylhistidine indicate loss of skeletal mass. Like muscle, bone is a dynamic tissue that not only provides mechanical support, but also aids in maintaining calcium homeostasis. External forces imposed by Earth's gravity are essential for bone growth, development, and strength. Bone derives its strength from bone makeup and geometry. 2/3 of the bone consists of calcium and phosphorus, with traces of sodium, zinc, and lead. The remaining bone is composed of collagen. Without the minerals, bone will become rubbery, and without collagen, bone will become brittle. Adaptations associated with the skeletal system during exposure to microgravity. In the absence of gravity, the external forces to which the skeleton is exposed are greatly reduced. As a result, bone synthesis is reduced. Bone architecture and composition are modified to accommodate the new lower load conditions. Calcium metabolism is altered, and bone strength may be reduced. Evaluation of bone mineral density in cosmonauts after a long-duration mission indicates that there was no change in whole-body bone mineral density, but there was a 4.2% increase in the skull compared to pre-flight values. Recent studies of cosmonauts on long-duration space flights indicate that bone loss in space is functional. It involves change in structure as well as demineralization. In microgravity, calcium is lost from bones at a rapid rate before plateauing at a higher steady state. Bone loss is variable and site-specific, with the highest losses occurring in the tendon-bone junction, calcaneus, lumbar vertebrae, femoral neck, and trochanter, with no losses from the arms and upper regions of the spine. Analysis of existing data suggests bone loss occurs at rates of 0.5% to 2% per month, depending upon the site. Two key mechanical factors which influence bone loss are load-bearing and muscle pull, as muscle insertion sites on lumbar vertebrae fail to exhibit signs of recovery when calcium has achieved equilibrium. In fact, the greatest loss of bone mineral occurs at the bone insertion site of muscle. Limited studies on cosmonauts using newer techniques and advanced computer analysis programs suggest that the bone recovery process after prolonged flights is incomplete, despite the fact that muscle mass and strength have returned to pre-flight values. Cosmonauts are instructed to perform 2 to 4 hours of daily exercise on the Mir treadmill, bicycle ergometer, or with their bungee cords 1 month prior to landing. The bone loss and recovery profiles suggest their exercise loads are inadequate. Although reduction in bone mineral density has been documented, bone experts suggest that the quality of bone is also reduced during exposure to microgravity. Bone quality, bone mineral density, and loading history are all important to study in detail to understand fully the bone response to gravity and microgravity. Possible physiologic mechanisms underlying skeletal deconditioning. The skeletal changes and adaptive response to microgravity are regional and vary between subjects. In the absence of gravitational load, two principal stimuli to the skeleton are altered: biomechanical stress and fluid pressure. Both factors may increase in the head and decrease in the feet. Thus, bone seems to be redistributed from the lower to upper body during spaceflight. The response of bone to mechanical loading occurs at the cellular level, but the mechanisms involved are not yet clearly defined. Alterations in calcium arise from the skeletal system being subjected to changes in tissue loading histories. The modest negative calcium balance is the adjustment made by the intestine, which reduces calcium absorption, and the kidney, which increases calcium excretion. These are major components of the calcium endocrine system. Upon return to Earth's gravitational stress, the reverse situation probably occurs, but has not been quantified. So in general, whole body mineral content tends to be conserved. Its distribution is altered or modified by mechanical forces and other factors. Measurements on Skylab and on the shuttle indicate that the spine lengthens by approximately 4 to 7 centimeters. This lengthening may be due to an increase of intervertebral disc height and by loss of the thoracolumbar curvature. It is documented that 68% of the astronauts experience back pain, and that sometimes this pain is severe and persists throughout both short and long-duration flight. Although the etiology of back pain is still unknown, some of the possible causes are increased intervertebral disc height and spine lengthening. Articulation and cushioning between the vertebral bodies of the spine is provided by the discs. The disc absorbs shock while allowing flexibility of the spine during various postures and activities. Each disc is avascular internally and consists of a negatively charged nucleus pulposus confined laterally by collagenous annulus. Physiological mechanisms that may cause back pain. During spaceflight, absence of gravity leads to skeletal unloading. This unloading increases water influx to the intervertebral discs, causing the discs to swell and the spine to elongate. Countermeasures for overall musculoskeletal deconditioning. Locomotion is the most common form of muscle activity, which generates the highest levels of internal and external reaction forces and provides the primary musculoskeletal load on the lower extremities. During terrestrial locomotion, peak ground reaction forces range from 2.0 to 3.5 times body weight. Current U.S. and Russian countermeasures to provide musculoskeletal loading include treadmill exercise, rowing, or biking exercise. However, none of these exercise countermeasures are able to generate one body weight of force at the feet for extended periods of time. In fact, Russian treadmills provide only 500 to 600 newtons of force, which is about half your body weight at the feet, and the bungee cords that the cosmonauts use are uncomfortable at higher force levels. Furthermore, currently used exercise countermeasures are time-consuming, 2 to 4 hours per day, and ineffective in preventing musculoskeletal deconditioning. Potential countermeasures for musculoskeletal deconditioning are exercise, both resistive and aerobic, human centrifuge, exercise against lower body negative pressure, pharmacologic agents. It is generally accepted that force levels generated throughout the skeletal system by daily activity are required to maintain bony framework. Research suggests that mechanical strains imposed by exercise and muscular contractions are important for maintaining and repairing ligaments and the junctions between ligaments, tendons, and bones. Aerobic exercise on a treadmill increases impact loading on bones. High mechanical loads also increase intramuscular pressure, which activates musculovenous pumping and thereby increases venous return to the heart. Aerobic exercise also improves circulation and metabolism, both of which are important for maintenance of all tissues in the musculoskeletal system. A potential alternative for generating gravity in space is a centrifuge. However, short-arm human centrifuges generate large blood pressure gradients along the longitudinal axis of the body and Coriolis effects which cause motion sickness. Moreover, centrifuges are very expensive and technically challenging to accommodate on board the spacecraft. NASA is also exploring the use of lower body negative pressure, or LBNP, to create a simulated gravitational environment in space. This will allow crew members to exercise aerobically and at higher levels of musculoskeletal force. This is needed to reduce exercise time. During exposure to LBNP, a static footward force is developed by the higher external suction pressure. Reaction force generated at the feet increases linearly with the magnitude of LBNP during upright standing posture and horizontal supine posture. Walking, jogging, or running on a treadmill within an LBNP chamber generates additional inertial forces from accelerations of the body center of mass. Such dynamic exercise increases tolerance to LBNP, which will enable astronauts to produce Earth-like reaction force at the feet over a short period of time. During exposure to LBNP, a compression suit may be required to provide a transmural blood pressure gradient similar to that produced in normal gravity to optimize cardiovascular stress and musculoskeletal stress simultaneously. Presently, exercise protocols and equipment for spaceflight are unresolved, although recent calculations suggest that all exercise in space to date has lacked sufficient loads to maintain pre-flight musculoskeletal mass. Force levels generated by bungee cord-assisted treadmill exercise are time-limited by harness discomfort. Furthermore, currently used exercise hardware does not exert enough inertial force at the feet, nor do they provide head-to-foot blood pressure gradients and transmural pressures similar to those found on Earth. Therefore, preliminary findings suggest that the gravity-independent technique of exercise during LBNP may provide Earth-like reaction forces at the feet and generate blood pressure gradients along the longitudinal axis of the body. Thus, by comparing some of the potential countermeasures, LBNP may be an effective countermeasure to help maintain musculoskeletal and cardiovascular systems of crew members during prolonged exposure to microgravity simultaneously. Studies of the musculoskeletal system in the absence of an external load can help determine cause of common Earth-based disease, such as osteoporosis and muscle atrophy. Osteoporosis can also reduce the quantity and quality of bone or muscle and result in tissue failure, especially in postmenopausal females and the elderly population. Space-related musculoskeletal research may also aid in improving fracture healing and other orthopedic diseases which are gravity-related. Use of lower body positive pressure is available for rehabilitation purposes and improvement of exercise equipment design on Earth. Unprotected in the vacuum of space, a human would survive for only a few minutes before swelling up. In the absence of an atmosphere, water vaporizes beneath the skin and is not able to escape as fast as it vaporizes. Astronauts also face extreme temperatures in space, ranging from minus 460 degrees Fahrenheit to above 300 degrees Fahrenheit. To survive the challenges imposed by such an environment, life support and protective systems that emulate Earth's environment are crucial. The fundamental purpose of life support is to create an atmosphere around the astronaut's body. The life support system used aboard the space shuttle is provided by a spacesuit. This spacesuit is a well-controlled, self-contained spacecraft that can support life for up to 8 hours. The main requirements for survival in space and harsh environmental conditions, such as the Moon and Mars, are oxygen, controlled temperature and humidity, food and water, waste management and protection against radiation and other hazards. Oxygen partial pressure must be maintained within a range of 160 to 760 millimeters of mercury. A minimum of 160 millimeters of mercury in the inspired breath is necessary to maintain 100% oxygen saturation of the blood. The temperature and humidity is controlled within the range of 64 to 81 degrees Fahrenheit. The heat production during sedentary or active metabolism ranges from 100 watts to 1,000 watts. Because we will need to work in space, it is important that we maintain a comfortable working environment. For prolonged periods in space, water is needed for food and beverage reconstitution, hygiene, and housekeeping purposes. It is estimated that for a 90-day mission with a crew of 6, the water requirements will be around 9,400 gallons. Small amounts of water and food will be necessary aboard the spacesuit as extravehicular activities, or EVAs, last longer. During active metabolism, astronauts produce trace gases such as sulfur dioxide and hydrogen sulfide, which need to be constantly eliminated. Other gases such as carbon dioxide are removed by a chemical called lithium hydroxide. The gaseous carbon dioxide reacts with the hydroxide to form a salt, lithium carbonate. This reaction removes carbon dioxide as fast as it is produced, and the suit gas, now enriched by oxygen from an onboard storage tank, is sent back into the helmet through a duct. Sweat is condensed by a cooling heat exchanger. This device cools and dehumidifies the gas before it is recirculated into the suit. Radiation can be hazardous to astronauts depending on the altitude and orbit of the shuttle. Polar orbits or other orbits that go up to high latitudes have trapped radiation. Radiation emitted by solar flares is intermittent. It can be increased to be life-threatening within minutes to hours. Other hazards that astronauts must be prepared for are meteor fragments and man-made debris in lower orbits around the Earth. These materials can cause potentially hazardous situations and must be shielded against. In addition to meeting all these requirements, a life support system must be safe, reliable, maintainable, and power efficient. When creating such systems, we must develop and demonstrate the system and its effectiveness. Next, we need to justify the design criteria. We then construct a prototype and prepare the system to be flight-worthy. All of these elements are important for having an efficient life support system that will be comfortable for long-duration use.
At Ames Research Center, we are an R&D group. We have to essentially project ourselves in terms of what the agency's needs are 10 to 15 years from now. The AX-5 represents a technology that was started in 1984 and completed in 1986, and since that time we've done extensive tests to meet the requirements of space station. Now, the requirements of space station are different than the requirements for a shuttle. They're much more severe. For example, there are a lot many more hours spent outside of the space station doing EVA than on shuttles, so therefore we have to provide more protection for radiation, more protection for debris and meteorite protection, and we also have to provide more mobility since the astronauts will be doing repair work on the outside. You won't be able to project exactly what it is you're going to have to do, so we have to provide mobility that's somewhat equivalent to shirt sleeve environment. Now, for the radiation protection, the suit is made of metal, and it's a double hull structure too, in that there is a double wall. The exterior wall for debris breaks up the debris, and the secondary wall keeps the debris from penetrating, and it also has more mass, therefore it provides more radiation protection.
The first EVA was performed to demonstrate that an astronaut can indeed survive in the harsh space environment with proper protective equipment. Although the suit incorporated a system of ventilation ducts that blew oxygen from the capsule over the astronaut's skin, This system was inadequate for cooling the astronaut while working in this pressurized environment. Therefore, a liquid cooling garment was added under the spacesuit to be worn next to the skin for the Apollo missions. The suit had to protect the astronauts from the hazards of the lunar environment and provide necessary life support for up to 8 hours while astronauts walked on the moon. This suit from Skylab was similar to that of the Apollo missions, but since the astronauts always worked near the capsule, life support could be maintained through an umbilical hose without an autonomous backpack. With the launch of the first space shuttle in 1981, suits were made in separate units of different but standard sizes and were assembled for each astronaut. The suit consists of modular components that can be combined to form a suit appropriate to individual anthropometric proportions. The suit includes a communication system that supplies voice contact with the spacecraft and ground control, as well as a display and control module that allows the astronaut control over the cooling system. A drinking water bag and urine collection device were also added. A lithium hydroxide canister is used to maintain the carbon dioxide partial pressure at less than 7.6 millimeters mercury at metabolic rates up to approximately 500 watts. A liquid cooling garment removes body heat by a combination of conduction, convection, and evaporation. A secondary oxygen pack provides emergency pressure, oxygen, carbon dioxide washout, and cooling for up to 30 minutes. The shuttle suit operates at 1/3 of the atmosphere, and there is a decompression procedure that astronauts must undergo prior to any EVA. Accordingly, the shuttle pressure is reduced to 10 pounds per square inch, and the entire crew, whether or not they will perform EVA, are subjected to this new lower pressure. This pressure is maintained throughout the entire EVA. For example, during the Hubble venture, a series of EVAs were performed over a 1-week period. The shuttle pressure was lowered to 10 pounds per square inch for the entire week. This minimizes bends problems similar to that experienced by deep-sea divers. Another important challenge to consider is biomechanics of body motion. Depending on what situation the suit is designed for, a spacesuit must fulfill basic human motion requirements. So the suit design must allow full range of motion with all degrees of freedom. For example, the hand has 36 degrees of freedom to work with. To design a glove for astronauts to perform intricate work can become quite complex. The current spacesuit has many shortcomings that preclude its use for routine space construction operations. New designs will allow a flexible system that will allow increased dexterity. Life support is also necessary during an emergency egress from the shuttle. A simplified life support system provides emergency breathing oxygen for astronauts during bailout. One recent spin-off application of life support systems involves an adaptation of the liquid cooling garment worn by astronauts. Children suffering from hypohidrotic ectodermal dysplasia, a disease in which they lack sweat glands, use the garment to maintain adequate body temperature. Research on multiple sclerosis patients has shown that reducing body temperature by only 1 degree Fahrenheit can temporarily improve nerve conduction. Hence, the liquid cooling garment is useful. Also, with the potential of large-scale environmental disasters, such as Chernobyl, various life support systems would enable crews to not only assess the damages, but to participate in helping fire crews contain the situation. By developing these types of life support systems, we can minimize the risks to the hazmat crew when operating in such hazardous situations. All of these breakthroughs have been facilitated by the curiosity and hard work of scientists engaged in the study of space. The success of NASA depends on our ability to attract talented scientists and promising researchers to participate in this effort.